How's it going, everyone? Welcome. Eulier Gonzalez here, and today let's going to now explore this particular concept known as trampoline, which is a recursion technique that when it comes to try to improve the memory anytime you do a recursive operations, okay? Why do we need to look and understand recursion? Because some problems that of course can be solved in an iterative approach, sometimes you don't know is the length of that. So what happened when those cases actually happen to, or when you need to implement an iterative approach using a recursion, which is a function that call in itself. And when you evaluate this recursion tool, it also is important to understand what is this tool can help us. What is the problem that this tool is trying to help us here? So by breaking down now the problem into sub problems, this might be sometimes the best approach and even the most performance and memory efficient to solve some particularly iterative, or when we need to look up for iterative solutions, right? Now, a great example of using recursion is by saying, hey, I want to call these functions, for example, in an nth amount of time. I don't know the nth amount, all right, per se or initially, but I know that that exists, right? This is useful, for example, for some data structures, like so binary trees or graph, where the idea is to look at how do you actually explore all of these different nodes on a tree. Now, because of that, all right, we need to look, or we so far look at what recursion is and what is the problem that recursion is. So based on Kyle Simpson's approach is that this is all about is I have now a problem that I could solve, a big problem that I could solve, all right? And I have now these specific problems that I'm currently that I can solve it. So we also look at, for example, the anatomy of recursion, which is that you need to define is a base case for that. And then the iterative or the function call or recursion of call or recursion approach for doing that. For example, count the number of vowels in a string, or define if this particular number is an anagraph, okay? And we look at more a practical approach in terms of why do we need to look at recursion and why recursion doesn't show up on production, because it sounds very good in theory but in practice is kind of off. Why is that? Because you have now this stuff that can happen, which is the call stack or the memory limits, the stack frame limits. Because at the end of the day, anytime that you call a function in JavaScript, is now is this execution environment, or the function execution environment that will contain is the variables and the parameters, which is it reserving a spacing memory for that JavaScript, and it's gonna do that over and 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 over. And if you don't define a well stop condition for your algorithm, then a lot of the time it's going to blow up. However, because now functional programmers back then, of course, when they don't have that fancy memory that we have right now, they only have is 4K memory. Doing a function call is something that is very, very expensive. So that's why, for example, in Internet Explorer 6, which is a browser that doesn't exist, they limit the amount of recursion call that you can do to some random magic number like 13. right? Which is preposterous. It's ridiculous. Why somebody Microsoft come up with that is a mystery. It's a puzzle, all right? But they say they think back then that, well, if you run now if you made more than 13 calls on the call stack, or if you add all of these frames to the call stack, at some point is something that is problematic, so they don't want you to go further. And browsers stop, because also browsers are very scary of what can users can do. So they put now a limit that is quite funny, because you can actually check what is the function call that particular browser allow you to, or the host environments allow you to. And from Chromium-based browser is something like 8,000 calls, where Firefox, SpiderMonkey, you can do that for 26K call. So again, it's very host environment dependent on the amount of call you can do, or this recursive or this recursion that you can implement, or you can at least go through without running to a range error. And why is that? Because if you have now a range, if you don't have this particular limit, what happens is that your browser and your OS will now shut down, because if they don't have any resource to allocate more memory, so it just turned off. So to prevent this, and because letting the users to do this kind of stuff is quite dangerous, because this also can lead to denial of service, so browsers implement this particularly range limits that it doesn't indicate that this is the reach. So you reach this range error is not because you reach the all available memory that the browser can allow you to. It's because they fixed that to a certain number based on implementation details. However, because anytime that you are calling a function, you create this particular frame on the stack, and we have now this idea of the stack that we're going to now put all of the work on top of that until the most top frame, and once that work is done, we will go backwards to actually solve all of the other to return to return the value, and therefore free memory and go back, and so on and so forth, right? So again, it is quite interesting. Most of the time, the technique, or the recursion technique that we need to use, is something called trampoline from the functional programming, and it comes because wouldn't it be nice to have at least not to call, or not to reserve a space in memory, that any time that we have to call a function in a recursive way, would it be nice to not create or save ourselves from to create this space in memory for all of these different functions that we call? It turns out that this is known as a proper tail call, where proper tail call, it's a, hey, if the function call is at the last of the operation, proper tail call, right? If this is the last of the operation, then they're going to, the JavaScript implementations, or the JavaScript engines, JavaScript developers from the JavaScript engine, they now implement these particular features, which is now this memory optimization. So proper tail call is a memory optimization when you do a function call in a recursive way, right? To solve some problems in a recursion way. So understand that is interesting, all right? And more interesting is using the technique called trampoline, that instead of creating all of these different stack frames, right? So this technique, what it does is to create now a function call, and then now call that function with the result, and then the trampoline now return back that result to actually call that function again, and so on and so forth and so on, right? So this is the different way they call this, like trampoline. So a function is never stacked on top of that, like a recursion JavaScript application. In fact, it's going to now switching back or jumping from function call to function return, and so on and so forth, and you get the idea. So even though that is quite deep, I must admit, and sometimes that won't give us too much value of this, so we can talk about the trampoline technique. Yeah, so we can talk about the trampoline technique here. So proper tail calls. So proper tail calls. Okay, so proper tail calls and trampoline and trampoline recursion technique. All right, which is something that you can see in Lambda libraries, for example, when you say, "Hey, trampoline, it's interesting. They don't even have this trampoline. What about this? They don't even use trampoline for that, because this has so recursion is like an educational topic. Recursion is like an educational topic, but it's more like to see how you can solve a problem in a recursive way, right? If you understand the problem of recursion, right? If you're able to describe the problem in a recursive way, that's what it is. So that to me is quite interesting. They don't even mention here on that, right? So trampoline in Lambda. Since JS doesn't have a tail called recursion, true, tail call optimization is what I'm referring to. Trampoline, I don't think if they add that to trampoline, no thanks. And it seems they add now to that library, but I don't see in the documentation, which to me is quite interesting not to see that, right? Trampoline, Lambda JS, right? Trampoline in Lambda JS. Okay. Oh, Lambda JS for Java. Holy and French toast. Trampoline in JavaScript 2013. So, but in any case, the point of this is something that is a particular library that you can use. We're not going to dive into this, because what we really care, all right, is to understand what is the problem that it's trying to solve, right? So we can focus now is on other tools that are relevant as a functional developer. That is list operation. Let's get into this, right?
If I go back to CPS, all right, moving right along, let's talk about lists. And actually, right off the bat, I need to clarify, we're not really only talking about arrays, although these kinds of operations are almost always illustrated using arrays, we're actually talking about data structures. The functional programming concept of doing operations is not limited to, oh, I can only do a map across.
Exactly. So this kinds of operations are not limited to one type of data structure, right?
Across an array, or I can only do a filter across an array. These sorts of operations like maps and filters and reduces are actually generalized operations that should be able to be performed across any data structure. It just happens to be, especially in JavaScript.
Exactly. So these kind of operations are not limited to one, or these kind of operations are not limited to one type of data structure. Okay?
That it's super convenient.
Exactly. It just happens to be that it just happens to be that it is super convenient to explain these kinds of concepts using arrays for that. But this is not only for, but this is a cross-sectional.
Is not limited to, oh, I can only do a map using arrays. We're actually talking about data structures. The functional programming concept of doing operations is not limited to, oh, I can only do a map across an array, or I can only do a filter across an array. These sorts of operations like maps and filters and reduces are actually generalized operations that should be able to be performed across any data structure.
Exactly, this one. But this, so this kind of a concept using array for that. But this operations exactly, this operation must be able to do in any, must be able to perform across any data structure. So must be able, exactly. So but this operation must be able to be performed on any, performed across any data structure.
It just happens to be, especially in JavaScript, that it's super convenient to illustrate in the context of arrays. So for now, we are going to look at them in the context of arrays, but then we're going to circle back and we're going to talk about this larger concept of adapting these ideas to general data structures. Essentially, what we're saying here is that there are operations that we've learned how to perform on single discrete values, and now what we'd like to do is adapt those operations, lift those operations, so that they work across a collection of values. There's a scary sounding functional programming term here that is heavily related, and it is called a functor. A functor is a value, and by value I mean could be a collection of values. It is a value over which those values in it can be mapped. So if we talk about an array, since we know we can call .map on an array, it's a functor. In fact, any data structure for which we have identified and defined a map operation, that constitutes or gives it the characteristic that it behaves as a functor. And I only use that word to demystify these words, not because I want you to go around and start talking about functor this and functor that, but rather that if you ever hear that word, I don't want you to be scared by that word. You just need to think, oh, essentially that's a value that I can map an operation across.
Okay, that's interesting. So a value or a collection of values. Okay. So a value or a collection of values, if you can apply a map operation, in other words, you can identify all of these elements and apply some sort of transformation to each one of them. This is known as functor. Let me actually ask Claw here a little bit, because that to me is quite interesting. Uh, yeah, that's the basic idea of a functor. Function and a functor. In category theory and functional programming. Oh, category. A functor is a structure like a container or a collection that can be mapped over, meaning you can apply a function to each value inside of without changing the structure itself. The map operation transforms the values while preserving the structure. Some examples of functors include list arrays, optional, maybe types, and promise and futures. For some time to be a proper function, it must satisfy two laws. Identity law, mapping with identity function, a function that returns its input unchanged should return an identical functor. And the composition law, mapping with a composition, a function should be the same as mapping with one function and then mapping with other. These concepts originate in the category theory and has been adopted in functional programming to describe data types that support this mapping operation. Hey, this data type, this shape of the data, can support now this mapping operation. Okay. And by mapping, we mean is that to apply a certain operation on each one value, and a map operation in this context is to be able to apply a transformation to each value without changing the structure, without changing the original structure. Okay. Without changing the original structure, aka giving you a new state of that. So a map operation in this context is able to apply any transformation to each value, and it happens to be that on lists, which is much more convenient to explain this kind of topics because it's much more easy to see them and to grasp on. So this is what a functor is. Is this data type? Okay, that's interesting. So we are demystifying all of this kind of stuff. So if this value or a collection of value, can you apply an operation, a map operation, aka a transformations to each one of those values without modifying the original structure? So in other words, if you can apply a map operation, if you can apply a map operation, a transformation of values, exactly, transformation of value, transformation of, or a transformation of each value. Okay, so in other words, if you can apply a map operation, a transformation of each value. So in other words, if you can apply a map operation So in other words, if you can apply a map operation, a transformation of each value with a transformation for each value, because it's not for each value, leaving the original structure intact. If you can apply map operation to a data structure, this is known as a functor. A data structure is a functor if you can apply a map operation to it. The map operation transforms each value inside of the structure, preserve the original structure shape, and return a new structure rather than modify its original map. So this is a functor. Okay. A data structure is a functor. Interesting. It's a functor. So a data structure is a functor if follow is this particular thing. As a functor. So a functor is a data structure that you can apply map operations, which is apply some transformations to it, maintain and keep the original structure of the original values, and create a new collection with the transformation.
Okay. So let's talk about map. What is map? It is fundamentally a transformation operation, meaning that we're going to take the values in some collection and perform a conversion on each of them. And remember that a data structure doesn't imply necessarily multiple values. A single value in a single data structure can be that functor idea, can be mapped over, and that's still entirely valid. It's just that we often illustrate it in terms of lists of values like I've depicted here. So the transformation, it's important to note that it's not happening in place. For it to be the functor, for it to behave according to these principles, it has to be a pure function. It can't be mutating this stuff. Your map transformation has to be producing a new data structure with the values having been transformed as they are projected to the new data structure. Okay? So if we start out with an array of 4 numbers and then we map that to a new array of different numbers that have been added or subtracted from or something, that's a mapping operation. The key technique, or the key takeaway here mentally, is that map always results in the same kind of data structure as it started with. You start with an array, map is going to give you another array. You start with an object, map is going to give you another object. If you start with a monad, map is going to give you another monad. Okay? The map always produces a transformed values, but the same data structure, same kind, same shape of data structure. Okay? That's a key takeaway. So how would we implement a very simple map transform kind of function for ourselves? Well, let's say that I had that's a key takeaway. The map always produces a transformed values, but the same data structure, same kind, same shape of data structure. Okay? That's a key takeaway. So how would we implement a very simple map transform kind of function for ourselves? Well, let's say that I had a list of strings and I wanted to turn it into a list of objects where those strings have been included. I could have a function called makeRecord. And makeRecord is a pure function because it takes in a name and it produces a new function back. And I'm going to use asterisks on that pure because we are technically doing an impurity with the unique random number generation or something. But from the perspective of passing in a value and getting back an object, it is giving us it's returning a value rather than mutating something for us. Okay? So if I do a map over the array Kyle and Susan with makeRecord as our map function, you'll notice that what I'm basically saying is call mapper with every original element, and whatever it returns, stick it in the new data structure. That new list that we then return, line 10, and that's how we end up with an array of objects. We have not mutated the original array of Kyle and Susan. Because arrays are the most common way that people think about these operations, there is built into the array prototype the equivalent of these operations. So we have a dot map on the array prototype. I can take that makeRecord and call it with my array directly with the array.map and use the mapper as makeRecord, and we'll end up with the same kind of thing, an array of those objects. So think about any sort of source value, any sort of conversion or transformation that you might want to do on that value to project a new value from it. We could take a number and map it with some sort of arithmetic operation and come up with a new number. We could take a string and map it with some kind of string concatenation where we're prefixing or suffixing the string. We could take a string and map it with a to lowercase or a to uppercase transformation, in which case we're making all the strings uppercase. We could take a single promise and map it into a return promise. We could take a string and turn it into a promise. Any sort of source value with any sort of transformation can be mapped, and any collection of those values can be mapped. One thing that is also important to point out is that the idea of map, the idea of the other ones that we'll look at, is that we are using the same transformation across all of the values in the data structure. So it's not the case that we do some of them, we map the numbers to strings, and some of them we map the strings into promises or whatever. That would be two separate, distinct map operations across subsections of our data structure. We pass in one mapper function, and it does one set of things. It is possible for your mapper function to have some sort of if statement logic in it, some branching logic in it, where it returns different things. But that's a sort of polymorphic way of thinking about it. And even though you might be able to do that, I'm going to strongly caution that a mapper function should do one thing. It should turn strings into numbers, or strings into promises, or functions into numbers, or something like that, instead of doing a bunch of polymorphic. And that's just a fancy way of saying branching based upon types. It shouldn't do a bunch of different things based upon different input types. That's generally not a great idea. Again, the key takeaway here is anytime I start out with a collection of values, like an array or an object, a collection of values, and I want to perform a common operation for all of the values that transforms them into some other kind of value and come up with a new data structure, then what I'm pattern matching in my head against is that's called a map. Our next operation that we want to look at, our next list or data structure operation is called
So filter operation. Okay, map transformation. Okay, filter, inclusion. Okay, map transformation. Map refers to transformation. And filter refers to inclusion.
filter. Now, filter is often referred to as, or thought of as, an exclusionary activity. So let me explain it or illustrate it in this way. How many of you have ever made spaghetti? Anybody? In my house, the only meal that I cook in my house is spaghetti. I can cook steaks and other meat on the grill or whatever, but the only meal that I make is spaghetti. My wife does all the other cooking, and she's great at it. But I like to make spaghetti, and I enjoy the process for some reason. And so in spaghetti, generally, you have a big pot of boiling water with your spaghetti noodles in it. And at some point, when the noodles are cooked, you have to pour out the water and keep the noodles, right? So what do? You take a strainer, you take a filter, you hold it over the sink, you pour everything in, and the water goes through, but the noodles are caught in the strainer, okay? Now, if I were to describe that process and ask you, would you be more naturally or would you be more normally inclined to describe that as filtering out the water or filtering in the noodles?
You say filtering out the
And
water.
I don't know what your particular answer is, but most of the time I hear people say, I would call it a filter out. I'm excluding the water,
Exactly.
and the noodles are what's left over, right? I'm not
The noodle was
including the
left.
noodles in my set, right? So we generally think of filtering as an exclusionary activity. And in fact, almost every place that you can think of metaphorically or in the English language, when we use the word filter, we think about it in terms of filtering something out. Which is exactly why, as programmers, we decided to actually implement filter as an inclusion operation. Just to mess with people. Just to make it reverse so that everybody gets confused. Because in filter, as it applies to programming, it's actually a filter in. And by that I mean, when you tell it whether or not you want to keep something, you return true if you want to keep it, and you return false if you don't want to keep it. So the true semantics sort of implies that I'm filtering it in. If I went to the grocery store and there was a big old pile of apples and bananas, and they were all mixed together, and all I wanted was the apples, and I had to sift through every single fruit, pulling out all the apples into my basket and leaving all the bananas, would you describe that as filtering in the apples or filtering out the bananas? Most people would say I'm filtering out the bananas. I only want the apples. If I had a list of numbers, 1, 2, 3, 4, 5, and I ended up with the list of numbers 1, 3, 5, that is the odd numbers, would you say that I filtered in the odds, or did I filter out the evens? The problem is that
The
we
problem
use this
is that
filter word.
is the way how
When
now
in English,
the
we mean
English
filter out,
would
but in
talk about.
implementation, we mean filter in. And I don't know if any of you all have ever had this, but I've had a bunch of bugs in my programs over the years where I was thinking filter out, and it was actually filter in, and essentially my Boolean logic was reversed. So I have taken to, in my own practice, I never use the method named filter ever again. I don't use filter. I either call it filter in or filter out because I don't want there to be any confusion in the program. What am I doing at this point? Am I filtering in things or am I filtering out things? I really wish we could just abolish the word filter because there's this baggage here. So we're going to build a filter in because it's going to work exactly like the filter that's on the array prototype. A filter in method, which takes a function. Remember up there I called that a predicate? Remember earlier in the course, rather, that I called it a predicate when a function returns a Boolean. If it returns a true false based upon some value input, it's called a predicate. So the way the filter works is it loops through the list of values and it calls the predicate. And if the predicate returns true, it includes it in the new list. Otherwise, it just ignores it. And then we end up with a new list. So what's an example of us filtering? Well, if I had a list of session objects, and I wanted to figure out if any of those, a list of user objects, and I want to figure out which of those users are logged in, meaning which of those have a session ID attached to them, then I could use a filter in, and the filter in is logged in, the function, the predicate up at the top. It returns true if there's a session property that's non-null on the object. So now I'm going to end up with a list of users that have a session object attached versus the ones that don't have a session object attached. That's filtering in. And we can do the exact same thing with the built-in filter method on the array prototype. It does the same thing. It takes a predicate function, returns a new array with the values included for which the predicate returns.
But this is interesting because it's about how you describe stuff.
The pattern matching for how to decide is
here.
filter the operation that I want to do is when I have some collection of values, some data structure like an array or an object, and I want to produce the same kind of data structure, but I want some of the values to be included and potentially some of the values to be excluded. Whether you think about that as a filter in or filter out is up to you. Hopefully your method names are unambiguous so you're not going to create bugs in your code. But the idea is I want to start with one collection of values and end up with another collection of values. The values don't get changed at all. That's what map does. So we're not picking new values here. We're just selecting implement filter as an inclusion operation.
Exactly, especially here in especially here. So in programming, the filter method or the filter operation is a filter in. It is an inclusion, right? Something that in English, a lot of the time we think filter, we think of it as filtering out, right? To exclude something, to exclude or discard something, right?
Just to mess with people, just to make it reverse so that everybody gets, I filtered out.
But the thing here is that we are now
returns a Boolean.
Filter in.
Returns a true false based upon some value input. It's called a predicate. Same thing with the built-in filter method on the array prototype. It does the same thing. It takes a predicate function, returns a new array with the values
is that we are now
included for which the predicate
including it. Filter, it means
the pattern matching for how to decide is filter the operation that I want to do is when I have some collection of values, some data structure like an array or an object, and I want to produce the same kind of data structure, but I want some of the values to be included and potentially some of the values to be excluded. Whether you think about that as a filter in or filter out is up to you. Hopefully your method names are unambiguous so you're not going to create bugs in your code. But the idea is I want to start with one collection of values and end up with another collection of values. The values don't get changed at all. That's what map does. So we're not picking new values here. We're just selecting values based upon some predicate check. Our third and final list/data structure operation that we're going to look at is called reduce. If map does transformation and filter does inclusion or exclusion, depending upon your perspective, reduce combines values. it's a different sort of an operation because it's not actually taking one individual value at a time and making some decision on it. The other two operate independently on individual values. For example, you could imagine implementing map or filter in an entirely parallel sort of scenario. You had 1 million values in an array, and you had a filter that was parallelizable across background threads. You could spin up 1 million background threads and do each filter operation entirely independent because the decision is made only on that value. Same thing with map. And in fact, in many scenarios, not JavaScript, but in many other functional languages, they do actually implement things like map and filter entirely threaded so that they can happen in parallel, at least for large data structures. But reduce can't really work that way because reduce works with multiple values. It makes its decision based upon the current running accumulator as well as the next value. So it's not really readily parallelizable or independently parallelizable.
It's like it's looking at these two sets of elements.
So here's how it works. We start with a collection of values.
Then you apply
and we need to start with some sort of initial value
to combine
that is appropriate for the list of values. So if we have a list, a collection of values. So if we have, for example, an array of numbers, and we're going to do something arithmetic with those numbers, like addition, a good initial value might be 0. If we were going to do multiplication, or even division, a better number might be the number 1. You with me? If we were going to start with a set of strings and do like some sort of concatenation of all the strings, a good initial value would be an empty string. If we were going to start with a list of promises and try to chain all those promises together, a good initial value might be an already resolved promise. If we were going to start with a list of functions and have one function call another and that function call another and so on, aka composition, we might start with the identity function as a good initial value. You with me? So you have to select an appropriate initial value for your reduction. There are some special cased implementations of reduce, another and that try to chain all and do multiplication or even division, a better number might be the number 1. You with me? If we were going to start with a set of strings and do like some sort of concatenation of all the strings, a good initial value would be an empty string. If we were going to start with a list of promises and try to chain all those promises together, a good initial value might be an already resolved promise. If we were going to start with a list of functions and have one function call another and that function call another and so on, aka composition, we might start with the identity function as a good initial value. You with me? So you have to select an appropriate initial value for your reduction. There are some special cased implementations of reduce which will, if you don't provide an initial value, they will select the first item in the collection as the initial value and start the reduction with the next value. That's a special casing. Not all implementations do that. That can be convenient, but not all implementations do it. So generally, the problem is you need to select a good initial value. And sometimes that's easy, like 0 or empty string, and sometimes it's a little bit more awkward. So you have to be careful in selection of your initial value. But anyway, what it does is whatever the current value, whatever the current accumulator is, either the initial value or if we're deep into the reduction, it takes the current accumulated value, and then it adds in the next value in our collection. Those two come in together, and somehow they get combined with a reducer. So they get combined. We take the number 3 and the number 4, and we combine them. We reduce them with addition, and that produces 7. So now our new accumulator is 7. Or we take two strings and we combine, we reduce them with concatenation, and now we have 1 string. So our reducer function, like we have a mapper and a predicate filter function, we have a reducer which takes 2 inputs now. Takes the existing accumulator and the next value in the collection, and that reducer decides how to combine them. Oh, and by the way, combination, the idea of reduction, it's a very general concept. Okay? You might think the only way to reduce 2 numbers would be to add them together or divide them or multiply them. But you could do a reduction that just picked one of the 2. For example, you wanted to pick out all the evens, you could do a reduction that just only selects evens. Right? So combination is whatever you define it to be. Reduction is whatever you define it to be. But it is oftentimes something where the values end up together in some way, like strings or numbers or functions or promises. Or whatever.
This is interesting because
so the way it looks is we start with an initial value,
eliminate a lot of these
stuff in, combining all of these down to a single discrete value. Often you would start with a, say, list of numbers and produce from a reduction a single number as a result. Or start with a list of strings and have a single string. But it is not always the case. Reduce is actually kind of the Swiss Army knife of functional programming because you don't even have to produce a single discrete value. You can produce another data structure from a reduce. You could start with a list of numbers and reduce that to an object with properties holding those numbers. Or you could start with a list of numbers and produce a whole different list of numbers. As a matter of fact, counterintuitively, a list of numbers could be reduced to an even longer list of numbers. Okay? So it's a very general operation. In fact, it's so general, and we're going to come back to this a bit later in this discussion, it is so general that both map and filter can be implemented with a reduce. Think about this for a moment.
If reduce, because it's the way of reduce works.
At each operation, I have an accumulator and I have a value. If my accumulator is a new list, it starts out empty, and I decide to put stuff into it, if I call the mapper function and I take the value and I put it in, the end result is a new list that's been mapped.
Exactly.
Or if I did an if statement with a predicate and only put stuff in if the predicate returns, the result of that reduction is a filter. So it's the Swiss Army knife. It can produce any of the other operations. Basically, any of the other operations can be expressed in terms of a
but reduction. A reducer is
powerful,
a combination.
But just don't get intimidated by it. You'll often just do basic reductions like.
So anytime you look at reducer is that, hey, we are combining this.
So how would we implement a reduce? Let's say that I had a list of lists. So I have a two-dimensional array here. These are basically, like a list of tuples. Remember we talked about tuples before? A two-element array. Well, I'm going to interpret my tuples as the first element representing a property name and the second element representing a value. And I'm going to reduce my list of tuples into an object. So here's my reduce, and you'll notice that my implementation of reduce is generic. It doesn't know anything about what I'm going to reduce over. It just knows that I'm reducing over an array and producing some new value. So we start with an initial value, and we call the reducer with the current accumulator, the ret variable. That's the current accumulator, and the next element, and whatever that returns becomes the next accumulated value. And we just keep doing that over and over until we're done. We can pass that a list of tuples, and if our add to record reducer up at the top takes in a record, and it takes in, that's our object, our running object that we're going to build up, and it takes in a tuple. I'm doing a destructuring there. This is partly just to be saving space on the slides, but I'm showing that my element is a tuple, and I don't really care about the tuple. I care about the key and the value in the tuple. So I've got a destructuring there that says, give me the key and give me the value.
And the tuple is in the special is what an array can and a tuple is what an array can look like. And a tuple is a fixed length, all right, where a list is, or an array is something that is with an undetermined that contains the same. So in objects, an array, you have two aspects of this. So you have tuples, which is fixed, and each one of those elements can be different, whereas lists, all of the elements are the same value, but the length is undetermined, right? You continue add elements to this, so on and so forth. Mm-hmm.
And I just make a new copy of the object. That's what ... record does. And then I add in the next key. That bracket key is the computed property name from key, and then I set the value. Why do you suppose I didn't just add the property to the object? Why did I make it?
And another interesting topic is that objects has two aspects of this in JavaScript. It can be either a record or a dictionary. So a record is a object that is an end list of, so a record in a dictionary, okay, a record in a dictionary, it's important, a record in a dictionary. Here is with GS. Let's get into this. Record in a dictionary, record in a dictionary, record. This is tackling GS, exploring here. Because this is as follows. Where is it? The nature of JavaScript now about form. Tuples, no. I think this is part of the statement, semicolon, identifier, statement, expression, statement versus expression. Mm. Statement and expression was allowed where ambiguous syntax. Mm-hmm. But I think primitive value versus object. There you got it. So for example, like record. No. I think this is on TypeScript. Oh, okay. Mm-hmm. Okay, so they changed that. That's interesting. And that is typing arrays. Is typing arrays, but this is more like a dictionary. Exactly. Exactly. It can be used, right? So a fixed layout object, which is known as a record, and a dictionary. So a dictionary is an arbitrary number of property whose names are not known at development time. All property have the same type. So the thing here is that a dictionary is something that is known in terms of type, but it has an unknown number of properties, whereas a record, okay, or a fixed layout object is that it contains now a fixed number of property, or a record, right, which is something they think they changed that. Yep, they changed the definition of that. So a record, a dictionary. So a record here, a fixed number of property. So a record contains now a fixed number of properties, okay, that are known at development time, and each property can have different types. So the subtle difference here is that records, each one of them can have different types, all right, but it's a fixed layer objects, and the other is a dictionary, which is a dynamic number of properties, all with the same type. Mm-hmm. Interesting. All right.
Keep a copy of the object every time.
Because you don't want to mutate the.
I don't want to mutate, right? If I just added the key to the object, we'd end up with the same result, but now we would have had basically an impure reducer, creating a side effect at each iteration on some single shared object. And that may or may not create bugs. In our particular case, it maybe would have been safe. But it's a terrible idea to ever assume that it's okay for you to just mutate a value that somebody else passed to you that you don't control. Remember, we talked in immutability earlier in the course. Anytime we receive a value, assume that you're not allowed to mutate it. You've got to make a copy of it if you want to extend it. So that's why we write the reducer on line 2 to make a copy of the object. Reduce, of course, is implemented on JavaScript arrays. Same thing. We start with an array we call reduce with our reducer, and then we give it an initial value, in this case, the empty object. I want to call something out about our reducer, because I want to call back to something we talked about earlier in the course, which was the shape of things. Remember, we talked about the shape of functions. Look at the shape of our reducer and compare it to, the shape of a mapper. The shape of our reducer is that it takes in 2 values. and produces one output. Whereas the mapper function takes in one value and produces one output. So a map function is unary, a predicate is unary, but a reducer is binary. And a little bit later in our discussion, the shape of these things, the relative shapes of them, is going to matter a whole lot when we're talking about trying to put things together. If they don't have a compatible shape, they don't fit. The Lego pieces don't fit. Okay? So remember, at the very beginning of this course, I said functional programmers love unary functions. The math, the way it works out, unary functions are just so easy. The Legos just work together. We can compose them. We can do all kinds of stuff. But when we have non-unary functions, the next best thing is a binary function that looks like this, which is a reducer. Okay? So essentially, any function that takes two inputs and somehow produces one output from those two inputs can be thought of as a reducer. It fits that shape as a reducer. And that's something I want you to keep in the back of your head for later on in our discussion. I want us to talk about composition for just a moment. Remember our reduce function. There's another companion function called reduce right. So reduce goes from left to right through an array, but reduce right goes from right to left. You might remember earlier in the course another thing that either went left to right or right to left. And that's not accidental. That's foreshadowing for this discussion. Remember we talked about a compose to. We did look in our exercise at the general compose utility, but just think about compose to for a moment. Look at the shape of compose to. What shape does it have?
Binary.
It takes two inputs, and what does it produce?
One output.
A single output. So what shape does that sound like? Sound like a reducer
so
to
like
anyone?
a reducer.
That's a reducer.
That's,
That can be used as a reducer. What reduction does it do?
Okay.
It takes two functions, and it reduces them through, what do we see on line 7? What is line 7 doing?
The execution of all of that, the output, the single
Look
output.
at specifically line 7. What is line 7 doing?
It's returning a function.
It's not. That's line 6. What is line 7 doing?
Is returning you a single output.
What is it called when one function gets called and its output gets passed to another function call?
Position.
Composition. That's a composition. When fn1 is called with a value and its output is immediately passed to another function and that one is called, that's called a composition. So the way that we are reducing those two functions is through composition. That's a valid way of composing. And what I want you to think about when you think about reducing is a valid implementation of composition. If I asked, write me a general compose now, instead of writing a for loop and keeping track of stuff, now you should be able to pull out, aha, I can just use a reduce right. We need to use reduce right because composition goes right to left. If I said, write me a pipe, you could pull out the dot reduce and reduce through using compose to as your composer. So here's what that looks like. We are doing reduce with the compose to, but we can actually implement compose with reduce right. Here I'm calling the list of functions, fn's, line 3, I'm calling reduce right. And the reducer that I'm using, I've named here invoke just because I couldn't come up with a better name for it. What it does is it takes two values, a function and a value, and it reduces that function and value through invocation. If you were to describe what is the composition, what is the reduction that is happening, line 4 is taking a function and a value and reducing them through invocation, which is to say passing the value to the function and then returning that result. So our reduction is an invocation.
The initial value
That's
in
how
the
we
function.
can implement a compose across a list of functions as a reduction, as a right reduction, basically. Line 9, we make f, which is the compose of div 3 mul 2 add 1. F of 8 gives us 6 because 8 plus 1 multiplied by 2 becomes 18.
Because here what you're doing is to reduce right. It's gonna round this function from right to left. Exactly. Which is now you pass the value 8. You're gonna add 1, which is 9. You're gonna multiply by 2, which is 18, and then divide that by 3, which is of course give you 6.
As some homework, I want you to write a pipe function for yourself and use the regular reduce utility, okay? All right, let's try an exercise to practice these list operations, actually data structure operations, but these list operations, map, reduce, and filter. And actually this exercise is going to include some other review of functional programming concepts that we've been learning up to this point in the course. So we're going to get a chance to bring in several different things, like closure and recursion and other things. All right, so the setup of this exercise is really important because if you look at the exercise file, It's basically empty. I haven't provided you anything because the instructions are very explicit on what you want to do. And unlike many times where I know the temptation is to sort of skip to the good parts of some exercise, it's really important that you follow each of these steps in order because they're taking through a derivation of problems that you need to bring in different concepts from our course so far to solve. So starting with 1, 2, 3, and 4, those are fairly straightforward. Item 5 on this list is where you're going to spend most of your time on this exercise. You're going to be writing an add-n utility that uses functions that you've created in items 1 through 4. But this add-n utility, you're going to implement it potentially multiple times. At a minimum, you need at least one working implementation, and you can implement it with a looping construct like a for loop or a while loop. You can implement it a second time using recursion. We talked about that a little bit earlier in the course, so you could use recursion to implement this. And still a third time, and this is really the important one for this particular exercise, you can use a functional helper like reduce. So at a minimum, I want you to implement it at least one time, try your hand at maybe 2 or 3 times, and definitely at least try it with the reduce. So you spend a pretty good significant chunk of time trying to get the add-in function to work there. Another little hint, it's not here in the README, but I just want to point this out. What you're going to be doing is dealing with functions all over, and that shouldn't be surprising. This is a functional programming course. But there's a temptation to want to eagerly reduce everything back to concrete values. And the temptation to eagerly reduce these partial sums back to concrete values is going to lead you into a much more awkward and less performing solution here. So think about what we've talked about so far in this course, the idea of deferring work by having things wrapped up in functions. That deferral of work till the end is actually the clue of how to get a much better solution to the add-in problem. And that's true regardless of which of the 3 implementations that you choose. Okay? So just keep that in mind, the idea of deferring work, deferring the adding until a later time. Keep everything at the function realm, and the solution will end up a lot easier. But that's not the end of the exercise. There's still items 6, 7, and 8 to go through. That's where you're going to, again, get more practice with our list operations like our filter, our map, and our reduce. Okay? So you should allow a pretty good chunk of time to work on this exercise. It is challenging. It is bringing not only the concepts from this unit of discussion, but also many of the things that we've covered up until this point. And so you really want to take your time and make sure you're getting all of those pieces right. Take definitely a good chunk of time to work on this exercise.
Absolutely. 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 Let's gonna take a pause here.